Okay, Assalamu alaikum, ya shabab. I hope everybody can hear me. Today, of course, we are going to have the online quiz. And basically, this time I planned everything. The quiz will start by itself and then ends by itself. I will be around, connected to the session through Zoom if you have any question as usual. But I am expecting that this experience will be much better than the previous one. Everybody should know where to go, what to do. So hopefully we'll not have any problems. The quiz time is just enough. So you should work hard on it to finish on time. The purpose of the 2 minutes is emergency. So some of you ask me to add 2 more or 3 minutes, something like that, for uploading. My expectation is that you can do this within 20 minutes and then less than 20 minutes, like 18 minutes, and then you have 2 minutes, 3 minutes for submission maximum. Okay, no emails today, ya shabab. We need to be good in this. This is a good exercise for all of you and for me as well, because on the 23rd, I think, of October, if I am not wrong, we will have our exam, the midterm. Okay. By the way, I would like to remind everybody about the project. I didn't check it this morning, but if you did not sign up in any group, please do so. I will send you another announcement about what will be the progress of the project. Most likely, ya akhwan, the progress of the project will be in terms of a presentation. You understand? So we'll ask you to deliver some task of the project through presentation, because we have already allocated, grades for the presentation. And instead of dumping all of this 15%, I believe, on the final presentation, we said maybe we'll do it like twice. This is gonna make it more fair for you. The only problem which I don't like about the presentation, I have to admit, is the fact that we will need a minimum of 1 lecture, and we are already late. So let's see how we can do things. We'll do the best, okay? Let's try to finish. By Sunday, we should finish this chapter. And maybe, if I'm optimistic, I think by Sunday we can introduce chapter number 4, okay? So last time we talked about the distortion energy theory, the maximum shear stress theory. And with the distortion energy theory, we basically stopped. I think my marker is not working. Just give me 1 second, ya shabab. Okay, can you hear me?
Yes, we can.
Okay, so we said about the distortion energy theory is that we call it the von Mises equivalent stress as well. And for a plane stress, for example, it is sigma prime. For a plane stress, this is the form of sigma prime. You can also solve it using principal stresses for plane stress, or for general state of stress, which is this one. Now, again, similar to the maximum shear stress theory, we are going to introduce a factor of safety, N. And N equals to the yield stress of the material divided by the von Mises stress. Okay, so imagine this. Always imagine that if the yield stress is up, it should be the maximum value. The one below it should be less than that in order to get a factor of safety greater than 1. if Sy doesn't change because it's a property of the material, unless you change the material. So you will see the state of stress and put it below. If that state of stress is so big, it will divide Sy by a big number, and that's when n goes to a value which is less than 1, which becomes not safe. Okay. Now, the distortion energy theory, if you try to predict the shear yield stress on it, using it, it will become 0.577 the yield in tension. If you remember, the maximum shear stress theory tells you, go and find Sy from tension and then divide it by 2, and that's how you can find the yield in shear. The maximum shear stress theory, the distortion energy theory, so this one is 0.5 multiplied by Sy. Is that correct? This is the maximum shear stress theory, Sys from the maximum shear stress theory. Now, Sys from von Mises theory, or the distortion energy theorem, is equals to 0.577 Sy. So it's a little bit off, a little bit, by 0.077. That's 15%. Okay, greater. So I know you may now think, okay, how can we use these theories? We're gonna have a comprehensive example in a minute. So let me show you the next theory. Next theory is the Coulomb-Mohr theory. This theory was introduced because there are materials which behave in asymmetric fashion. What does that mean? It means that their yield in tension is different than their yield in compression. You got my point? And what happened? Well, some materials are stronger in compression, some materials are weaker in compression, and vice versa. We don't know. So what happened is this. The Coulomb-Mohr theory, or sometimes called the internal friction theory, okay, states the following. It says that go and find the principal stresses. So you need to find them. You can't use sigma x, sigma y. Only distortion energy theory allows you to do that. And then if the first principle is in tension, of course, here, ya shabab, we're gonna have the 3 cases when you have all of the Mohr circle in the tension, all of the Mohr circle in the compression, or the Mohr circle is in between. But the theory in general says that if sigma 1 is the positive principal stress, then you should divide it by St, which is the yield in tension. Why are we calling it St, not Sy? Because we want to tell you that when there is, you can actually use this not only for yielding, also for ultimate. Which means if you, for any reason, want to use the ultimate strength instead of the yield strength, you can do that. And another thing is that when we use St, we tell you, oh, they are in this condition when the yield in tension is different than the yield in compression. Okay, so, and then you divide this, the third principle, okay, by the compressive yield or the compressive ultimate. Okay, so you take sigma 1 over St minus sigma 3 over Sc, which is equals to 1. Okay, now if you have the cases when the Mohr circle is positioned in the positive side, again, this is the same story, then you should worry only about sigma 1, which is you will compare this with sigma in tension. Why? Because both of them are in tension. So just look at sigma 1 and compare it with the yield or the ultimate in tension. That's it. Over here, we have a Mohr circle, which is in compression. So what are you going to do? You will worry about this principle, which is sigma B, and you will compare it with what? With SC. Why? لأنه يا شباب, this is in compression, this is in compression. الآن there is no tension. So forget about tension. Just look, does sigma B approach the ultimate or yield in compression, which is our limit? Does it approach it or not? If you have both of them, and you need to be careful. Why? Because if you plot, let's say that we have a material with sigma yield and tension is here, and sigma compression is there. Okay, let's assume that. Then what happened is this. Maybe the Mohr circle is here, maybe it is here, maybe it is here. We don't know. You are in between. You want to know both values and take them into consideration. Of course, I did some error over here. I want you to be careful about this. We should try to understand that whenever we write S for stresses, we indicate property. It is not a stress, it's a property. Property of a material doesn't change. You can change the stress that you apply on a material, but the property of the material, you cannot change it. Okay? So, interestingly, ya shabab, if you plot this equation, assuming that the material has bigger compression strength than in magnitude than the tension, then what happened? You will write ST here. This is, for example, 100 and 100, and the yield in compression, let's say it is minus 400 and minus 400. Again, like the maximum shear stress theory, we will have two constant lines bounding the boundary, and then we will have two linear lines in between. طبعا, there is no doubt, some materials might have, for example, 300 and 300, and they have maybe 100 negative and minus 100. That's possible. Okay, so you will have a little square over here and a big one there, and then in between you draw the line. Again, if you find sigma 1 and sigma 2 and then sigma 3, and then you determine which is sigma A and which is sigma B, you will go and see, are you within the envelope, or for any reason, if this is out like this, you are outside. Then if you are outside, then you are not safe. This is a graphical way to tell whether you are safe or not. You understand, ya akhwan? Now, so if we want to write this theory as a design function now, which is the most important equation, it's going to be sigma 1, okay, over ST minus sigma 3 over SC equals to 1 over N, where N is the factor of safety. If you want to find the shear yield for this material, which behave differently in tension than in compression, then it is the yield in tension multiplied by the yield in compression divided by their sum. That's the prediction of the yield stress for the Coulomb-Mohr theory. All right. Now, I remember I showed you this before. This is a comparison of the von Mises theory and the maximum shear stress theories, and those little dots around are experimental values. Okay, so sometimes you can see that some values are close to the maximum shear stress theory, and of course there are also many values that seems to opaque the von Mises, okay, theory. Now, let's go over this in like 3 minutes, okay? And then we'll have the next 2 minutes just to get ready, because in 5 minutes the quiz will start. So what do we want? We want to compute the factor of safety based on the distortion energy theory for location A and B. As you see, this is A and this is B. The bar is made of AISI 100 cold drawn steel, and it is loaded with a force 0.55 kilonewton. That's the force. And then we have a P force, which is 8 kilonewton, and a torque of which is 13 Newton meter. Now, what I want you to understand is that the question, what does it say? It says you want to find the factor of safety for point A and B. So somebody might ask, if I look at the cross-section over here, this is point A and this is point B. And I want to find NB and I want to find NA, the factor of safety. Now, this question by itself teaches you one thing, that there is ultimately infinite number of factor of safety. There is a factor of safety for this point, factor of safety for this, for this, for this, for this, everywhere. Why? Because each point, because stresses field and it is changing everywhere in the cross-section, I can compute the value of the stresses for each point, and from each point I compare it with the yield and I get the factor of safety. That's how it would work. That's how it would work. So let me, in summary, give you what happened over here in a little bit, okay? So we will have sigma x coming from the bending, okay, and from the tension. What is the bending equation? MC over I. What is the tension? It is F over A. As you remember, we have a cross-section which is subjected to a load P. So this is actually going to be P. And the area is this. This area. Okay? Now, also, I have a force like this, which is going to cause what? Bending, that will introduce tension in the top and compression in the bottom. Of course, in the middle, there will be the neutral axis. So point B will not have any bending. Is that right? Now, so we will pick, for example, point A and analyze it. We'll have tension and bending. And then also point A will have torque, which is TR over J. After that, I can write the element, okay, which is, طبعا point A يا شباب is located on the top like this. That's point A. So when I look at point A, I will see that there is sigma X on it and there is shear. بس خلاص. Once I have sigma X and shear, I can go plug them into sigma prime equals to sigma X square plus 3 tau XY square under the square root, and I find sigma prime. When I find sigma prime, I go and I say N equals to the SY over sigma prime. I repeat the same thing for point B. I think it's time, ya shabab, for the quiz.